It's a great pleasure and privilege to be here. Can you hear me with this microphone?
Yes.
Okay. And I'm going to talk about what's been achieved and what we may achieve in the next 20 years, or maybe even more. But let's remind ourselves why we do astronomy. We want to find out what's out there, just exploring. We want to interpret what we see in terms of known physics, perhaps new physics as well, and to understand how, from a simple beginning, our universe evolved to its present complexity, and perhaps to understand at a more philosophical level why the universe is the way it is. I'm going to start with a historical flashback. This is the best student we ever had at Cambridge University, Isaac Newton, of course. And among many other things, he must have thought about space travel. This is a famous illustration from one of his books, where he imagined a cannonball fired from a mountain top, and if it's fired fast enough, then its trajectory curves downwards, no more steeply than the Earth curves away underneath it. It goes into orbit. This is still, I think, the nicest way to explain the concept of orbital flight. He calculated that you'd have to fire your cannon at 18,000 miles an hour, far beyond, of course, what could then be done, and that wasn't done until the Soviet Sputnik in 1957. Things then proceeded apace, and 12 years after that we had Neil Armstrong's One Small Step, and I treasure this picture signed for me a few years ago by 7 of the Apollo astronauts. Neil Armstrong didn't sign this, but I did once give a lecture when he was sitting in the front row. Great honour, seemingly taking notes, or maybe doing the crossword, I don't know. But it was a great honour to meet him. Now, of course, had the momentum of the Apollo program been maintained, there had been footprints on Mars long before now. But of course, as we know, people since that time have only been in low Earth orbit. But unmanned space probes have beamed back pictures of the varied and distinctive worlds of our solar system. I'll give you a quick tour. If you were heading outwards from the Earth, and you look back from, say, 5 million miles, you'd see something like this, the Earth and the Moon with the sun shining from the right. You then get to the red planet, Mars, on which several probes have landed. This is the Curiosity probe that landed about 4 years ago, the size of a small car. And it landed where the oval is, in the top left of this huge crater. And it's been trundling around this crater for 4 years' time, studying the geology. And if you look near the bottom, you can see the track marks of it. It's been about 30 miles so far, and is still going, and it'll eventually climb that mountain in the center. Sending back pictures like this of the geology. Going further out, we get to Jupiter, with the 4 famous moons discovered by Galileo, all very different, actually. This is Io, sulfurous and volcanic. This is Europa, which has an icy surface and perhaps liquid underneath it. We then get to Saturn, with its rings, observed by the Cassini spacecraft. This is a rather nice picture, which shows an eclipse of the Sun by Saturn. This was taken by Cassini when it was beyond Saturn, lined up so that Saturn blocked out the Sun, but the Sun is still shining on the rings. And the Earth is just there. You can't quite see it. It's a long way away. And Saturn has a range of moons. This is Enceladus, a icy moon of Saturn, and by a close flyby of this moon by Cassini, they detected a gravitational anomaly, so we know there's an ocean under at least one side of this moon. And then we've had, in the last couple of years, 2 important probes of the outer solar system. One was the ESA Rosetta probe to the comet. It's landed a robot on this comet. And the other was the New Horizon probe, which sent back pictures of Pluto. And here's Pluto, here's another picture of Pluto, and there's Pluto and its moon Charon. These were huge technical achievements. Pluto is 10,000 times further away from us than the moon is. And this was done using 1990s technology, because both the New Horizons probe and the Rosetta probe took 10 years on their journey to get to their destination, and of course there were years in the planning stage. So if you just think how mobile phones have changed in 15 years, think how much better we could do now, and how much better we will do with miniaturized probes to the bodies of the solar system in the coming 20 years. What about the role of humans going into space? This is Schmidt and Chernin. These were the last two men on the moon in 1972. And the question is, will people go back to the moon? That's really the topic for another talk. Perhaps they will. Perhaps we will have Martians within a few decades. In fact, there is a plan to allow people to fly around the backside of the moon and come back. I was told they sold a ticket for the second flight, but not the first flight. But they will go in a few years, and the next step will be for people to go to Mars with perhaps one-way tickets. And I think there will be bold adventurers who will want to go. But they will go for an adventure, because as robots get better, the practical case for sending people gets weaker all the time. So they will go, in my view, as high-risk adventurers funded by private companies. Well, one question, of course, which we want to ask is there any life out there already before people get there? Well, there could be freeze-dried bacteria on Mars, or something swimming under the ice of Enceladus or Europa. But the prospects for any very exciting life look rather bleak everywhere in the solar system. But not if we widen our horizons beyond our solar system to the realm of the stars. And here we have huge developments in the last few years, and perhaps the hottest current topic in astronomy is the realization that many other stars, perhaps even most of them, are orbited by retinues of planets, rather as the Sun is. These planets aren't detected directly, but they're inferred by precise measurements of their parent stars. One way is to look for the wobble that's induced in the star by an orbiting planet, by precise Doppler effects. But the other way, which is found even more, is to look for slight dimmings in the brightness of a star, which are induced by a planet transiting across it. The theory is very simple. If the planet moves across, then it blocks out of the starlight, so you'll see the star dimming, and the dimming will be repetitive each time the planet comes round. And if you look from a long way away at the Earth transiting across the face of the Sun, the dimming will be 1 part in 10,000, because the Earth's about 1% of the radius of the Sun, 10 to the minus 4 of the area. Well, this technique has been wildly successful using this NASA Kepler spacecraft, which spent its first 3.5 years pointing at an area of sky about 7 degrees across and measuring the brightness of 150,000 stars in that part of the sky with a precision of 1 part in 100,000, looking for these dips. And of course, from the data, you can infer what the year of the planet is from the frequency of the recurrent dips, and also the size of the planet from the amplitude of the dip. And this is a rather silly depiction which shows a lot of the planets found. These are scales of the size of the planet. But there are many thousand planets that have been found. But I want to mention two especially exciting ones. One is the discovery that the nearest star, Proxima Centauri, which is a very faint dwarf star, about 100 times fainter than the Sun, is orbited by a planet which is about twice the mass of the Earth, probably. And this planet is in a habitable zone in the sense that it's at a distance from its star such that water could exist, neither boiling away nor staying frozen. Of course, habitable doesn't mean inhabited. I'll come back to that in a moment. But that's very exciting that even the nearest star has this planet. And even more interesting is what was reported just a couple of weeks ago. This is a star called Trappist 1. I won't explain the acronym Trappist, but this was a star, again, a dwarf star rather like Proxima Cen, which is about 40 light years away, and it was observed, and it's got 7 planets orbiting it. And the orbital periods are given there. They range from 1.5 days to 12 days, so the year would be pretty short on these planets. But because the star is so faint, the outer 3 definitely are in the habitable zone, in the sense that water could exist. But if you were on one of these, it would be a very different situation from being on the Earth or in our solar system, because this is a really miniature system. It's a very faint star and the planets close in. So if you were on one of these planets, you would see the other planets zooming across the sky, looking in the sky bigger than the moon or the sun do to us. So you have a very exciting astronomy in this. And incidentally, there's something which Newton would have found very interesting about this system, which is that the orbital periods are in fact not random, they're in simple ratios. There's a resonance between the orbits, and this is a phenomenon that's been found for Jupiter's moons as well, and the orbits arranged so that there are simple multiples in the numbers of revolutions that one makes while the other's going around. So there are resonances between the orbits of 6 of these planets. So it's a quite remarkable system. And this shows the dips, the transits for the different planets. Incidentally, the history is that this system was found by a Belgian-led group using a 23-inch telescope in Chile, but then it's been followed up with other telescopes, and the best transit data shown here comes from the Spitzer Space Telescope, looking infrared. So there's no doubt that these 7 planets exist. Well, what we want to know is, what do they look like? This is an artist's impression, of course. What would it be like on them? And is there any life on them? And what we'd really like to do, of course, as a start, is to actually directly observe these planets, not just their shadows, not just their effect on their parent star. And this is something which we can't yet do except in a few cases. To understand why it's so hard, supposing that you were aliens with a big telescope, say 50 light years away, looking at our solar system, then you'd find that our sun looked like an ordinary star, and the Earth would look, in Carl Sagan's nice phrase, like a pale blue dot, very close in the sky to its star, our sun, and billions of times fainter. But if you could observe that pale blue dot from 50 light years away, you could infer quite a bit about it. The shade of blue would be slightly different depending on whether the Pacific Ocean or the landmass of Asia was facing you. So you could infer there were continents and oceans, you could infer the length of the day, something about the seasons, and perhaps even from spectral data some evidence that there was something green on the surface or some evidence for non-equilibrium chemistry in the atmosphere. Well, we can't do this yet, but we will be able to do this for some of the nearest planets, maybe with the James Webb Telescope, but also with the high-resolution spectrograph on this instrument. Many people here know about this. This is the European Extremely Large Telescope. Europeans aren't very imaginative when it comes to nomenclature. And this is now being constructed in Chile, and it's got a 39-meter diameter mirror, not one sheet of glass, but about 800 pieces in a mosaic. And that will be able, in 10 years or so, to make observations and get some spectral information about planets orbiting nearby stars. Well, what about life? This is a question that all astronomers are asked. One thing we know is that most stars have planets around them, and at least 1 in every 6 stars is thought to have an Earth-like planet. Earth-like in the sense of being the size of the Earth and the temperature of the Earth. But, of course, that doesn't tell us the likelihood of life, because we know very little about how life began on the Earth. We don't know whether it was a rare fluke or whether it was something which would have happened in any given environment. We don't know either whether all life has the same chemical basis, DNA and RNA, as life on Earth, or a different one. But I think in 10 years, or 15 years at least, we are going to pin down this in two respects. First, serious people are now working on the origin of life. Serious biochemists. It's not relegated to the too difficult box when it's premature. People are working on it. And they will help to answer the question of the likelihood. And we may, as I mentioned, find some spectroscopic evidence for life on some of these planets. And that's simple life. But of course, even if simple life were common, then everyone asks the question, what's the chance it evolves into something complex, something even intelligent? And that, of course, is a separate question. We've no idea whether that would happen, and that's much higher risk. But we think it's worthwhile. In fact, a Russian investor called Yuri Milner has committed $100 million to a 10-year search to do a deeper search by various techniques for evidence of some extraterrestrial signal. No one's holding their breath for success, but I've agreed to chair his advisory group for this, and I think it's better he should spend his money this way than on a football team or a big yacht, which some of his contemporaries do. So I think it's good, but no one holds out any hope of this. But it would be crucially important, of course, if there were some detection showing that concepts of logic and physics weren't limited to the hardware in human skulls, as it were, or some sort of artifact. But of course, if these searches fail, then we can be less cosmically modest, because our Earth, though small, may be very special. But since we're in Durham, I thought I'd give this lovely quote from Thomas Wright, who speculated about whether there might be alien life very common, and he was comforted by the fact that in the cosmic perspective, what happens to us doesn't make any difference. And I think few of us can be quite so resigned, because being human beings ourselves, we care a bit about what happens to us, irrespective of what's happening in the rest of the galaxy. Well, I'm now going to jump from small-scale things in the universe all the way to the very largest scales, jumping over what's been talked about in two of the earlier talks. And I'm very sorry that because of train problems, I wasn't here to hear the earlier talks. But what we've learned is that these extrasolar planets are a sort of new Copernican revolution. Our solar system isn't unique. There are billions of solar systems in our galaxy. And, of course, we had the other Copernican revolution 100 years ago nearly, when we realized that galaxies like this were the dominant constituents of the universe, and there were not only billions of stars in our galaxy, but there were billions of galaxies in the universe. And this is a picture showing the Hubble Deep Field just in a domain a few arc minutes across. You have these hundreds of galaxies. It would take dozens of pictures like this to cover the area of the full moon, and this illustrates how many galaxies there are. But I want now to leapfrog to even bigger scales that we talked about, and ask the question, is the part of the universe we can see the dominant part of physical reality, or could there be something beyond it? Well, there is a limit to what we can see. There's a limit to the number of galaxies we can observe, which is essentially set by how far light's been able to come through the expanding universe since the first galaxies formed. It's a well-defined horizon to our observations. But that horizon, given that our universe is fairly homogeneous, has no more physical reality than the horizon around you if you're on the boat in the middle of the ocean. In that context, you don't think that the ocean ends just at your horizon. It may do, but you think it may go on a long way. And this is the same attitude we should take towards the universe. There's no reason to think it should should end. There's quite good reason, actually, to think it probably goes on at least 1,000 times further than we can see. That's because the gradient between what you see in that direction and that direction is very, very small, and so if there's some finite structure, it's probably much bigger than the little region we can detect. And it could go on so much further that all combinatorial options are replicated. So there could be another lecture room like this somewhere far, far beyond our horizon. And we will all have avatars, and it may be some consolation that if we make some kind of goof, we've got an avatar far away who's behaved more wisely. So there could be a lot more beyond our horizon. And incidentally, in an accelerating universe, we know that galaxies are disappearing over our horizon, so even the most conservative astronomers have to assign reality to galaxies that we can't even in principle observe. Now, I've talked so far about the aftermath of our Big Bang, but it's possible that our Big Bang is not the only one. And this is another cartoon which shows bottom right our part of space and lots of galaxies beyond our horizon, but this may be just one island in an archipelago of many, many universes. This is the version eternal inflation, which is a version of the inflationary model that we heard about in the last talk. And this, according to this idea, there are many, many of these domains. And I should have my hazard sign here because we're now going to talk about speculative physics, which may take at least 20 years to sort out. And the big question is, even though we know that the laws of physics are the same everywhere we can see, atoms in a distant galaxy have the same spectral features as nearby galaxies, it's not at all clear that will be true of this vaster domain, in particular the aftermath of other Big Bangs. And one possibility, therefore, is that they might be different. And it will be interesting, therefore, let me just... yes, and so there's an important issue which is something should be settled sometime this century. How many Big Bangs are there? Are there one, or is there many? If there are many, are they all governed by the same laws, or is there variety in the physical laws? These are two fundamental questions. And I want to just ask the sort of question that arises if you imagine a universe governed by different laws. Well, of course, it's easy to imagine these things, and of course, some people don't like this idea. They don't believe in this so-called anthropic reasoning. But for them, I would just say one thing. Imagine it just like the way historians do counterfactual history. They ask what would have happened if the Brits had been more effective in 1776 and had kept the American colonies, and biologists say what would it be like if the dinosaurs hadn't been wiped out. Would humans have ever evolved? So take it in that spirit. And let me just give 3 examples of what a universe would be like if we changed some things. First, suppose gravity had different strengths. There's a big number in astronomy, which is about 10 to the 40th, which is the ratio of the electrical to the gravitational forces between 2 elementary particles. And it's because that ratio is so large, because gravity is so weak, that stars have to be so big. If you imagine building up bigger and bigger objects, a sugar lump, self-gravity unimportant, a lump of rock unimportant, asteroid unimportant. When you get up to the size of a planet, then gravity makes it round. Get up to the size of Jupiter, gravity crushes it. 100 times Jupiter, you get a star. Now, stars are big because gravity is weak. If gravity was not quite so weak, if this large number was, say, 10 to the 30, not 10 to the 40, you would have a small-scale speeded-up universe. You'd have stars, gravitationally bound fusion reactors, but they would be less massive, they would live less long. So you could imagine a universe with different gravity. Supposing the laws of microphysics were different. We know that the periodic table exists because of a balance between the electric forces, which are disrupting a complex nucleus, and the nuclear forces. If the nuclear forces weren't so strong, we could have a dull universe where there was just hydrogen. if that was the case, then the large-scale universe would look the same. You'd still have stars, you'd have galaxies, etc., but they would have no fuel apart from gravity. So the universe would look large, but there'd be no complex chemistry, and it'd be rather dull, and probably would have no life unless you have something like Fred Hoyle's black cloud. It would bear the relation to our universe. I'd like to say that a marble statue bears to a real human being. It would look the same in large scale, but very different. And a third number is the lumpiness, which we heard about in last talk. We know that the universe is slightly lumpy, and that determines the scale of structure in the universe, a number called Q, which is about 10 to the minus 5. If that was a smaller number, we'd have very small-scale anemic galaxies. If it was too big, we'd have a chaotic universe. So one can do these counterfactual arguments, but I think they're only going to be of interest if we can get a firm view of whether these alternative universes exist, and also from string theorists and others about whether the laws of microphysics are uniquely determined by some fundamental laws, or whether there's a deeper level of fundamental laws, and what we observe is just a parochial bylaw in our cosmic patch, as it were. Our cosmic patch is as big as astronomers can observe, but could be still a tiny fraction of physical reality. Another flashback, this is Kepler. He, of course, believed that the orbits of the planets were in ratios given by the Platonic solids. That is wonderful theory. Now, we now know that that's not the right way to think of the planets. We now know that the orbit of our Earth is nothing special. It's just one of many planetary orbits, but it's not too eccentric, and it's at the right distance from a stable star to allow life to evolve. And we may be due for a similar grander transformation in realizing that what we think of the laws of nature, which govern the entire observable universe, may, in this far grander perspective, be just parochial laws in our cosmic patch. Well, we don't know. This is just the... how much longer do I have? 5 minutes. 5 minutes. Okay, yes. It depends really on whether this idea of an archipelago of universes stands up. And we don't know. It's speculative, but it's being studied now. And I'd like to recall that I was on a panel at Stanford University about a decade ago where we're with Andre Linde and others, and we were asked, how much would you bet on this idea of there being many Big Bangs, given that the physics is speculative? And I said, well, on the scale, would you bet your goldfish, your dog, or your life? I was nearly at the dog level. Andre Linde on the panel said, well, he'd spent 25 years working on this model of eternal inflation, which I should not go to. So he'd more or less bet his life on the whole thing. And later, on being told this, the great physicist Steven Weinberg said, well, he liked the multiverse idea, and he'd happily bet Martin Rees' dog and Andre Linde's life. Well, I'd just like to finish with two thoughts. One, this is a famous Ouroboros picture which indicates the links between the very small on the left, the quantum world, and the gravitational world on the right, and indicates why we can get by without a theory of quantum gravity in general, because chemists don't need to worry about the forces between gravitational forces between the atoms in a molecule. Conversely, astronomers don't need to worry about quantum fuzziness in the orbit of planets. But I want to say two things about this picture. One is that if you really want to understand the very beginning of the universe, we do need to have the synthesis symbolized gastronomically at the top between the quantum world on the left and the world of gravity on the right. That's why a theory of quantum gravity is needed. But I'd like to also mention that there's something important at the bottom. Things that are very complicated. And I think it's important as a piece of modesty for us to realize that only 1% of scientists are either particle physicists working on the left or cosmologists and astronomers working on the right. 99% of scientists work on the third frontier, neither the very large nor the very small, but the very complicated. And the most complicated things are things like us. And even an insect is more complicated than a star or a galaxy. And as some of you may recognize, this is the flea from the book Micrographia produced by Robert Hooke, who was Newton's least favoured colleague in the Royal Society, but a wonderful draftsman. And even the simplest insect is far more complicated, far more challenging to understand than an atom or a star. And we need to understand both the large and very small. We need to understand the atoms that make us and the stars that made those atoms. Well, just to finish with, I'd like to draw back from the entire cosmos, or a whole family of cosmoses, closer to the here and now, and answer a question I'm often asked: does being an astronomer give you any special perspective on the everyday world? Well, as I said, I don't think we're as relaxed as Thomas Wright about the fate of humanity, but I think there is one perspective we do have which most other educated people don't have, and let me just explain this to finish up. Most people, unless they happen to live in Kansas or parts of the Muslim world, are happy with the idea that we are the outcome of 4 billion years of evolution, as crudely shown in this time chart here. But I think most people, even those familiar with Darwinism, think somehow we humans are the culmination of it all. But no astronomer could believe that, because astronomers know that the time lying ahead is at least as long as the time that's elapsed up till now. This is a time chart of the sun's evolution. It's been shining for 4.5 billion years. It'll be another 5 or 6 billion before it flares up, becomes a red giant engulfing the inner planets. And the expanding universe may go on forever. To quote Woody Allen, eternity is very long, especially towards the end. So we could be nearer the beginning than the end of cosmic evolution. And that future evolution is going to be even faster than we've had up to now. It'll be on a technological timescale. We will control it. It may be electronic rather than organic, but we are not the culmination of evolution anywhere but. So any entities or creatures which are around to witness the death of a sun in about 6 billion years from now and send this postcard, they won't be human. They'll be more different from us than we are from a bug, because there's been far more time for evolution and much faster evolution. But my final thought is this, that even in this huge perspective, a concertina perspective stretching billions of years into the future and back into the past, this particular century is very special. It's the first in the 45 million centuries that have elapsed on the Earth where one species, namely ours, can control what happens, where we can perhaps trigger an extension of life beyond this Earth, maybe a transition from organic to electronic intelligence, or on the other hand, by misadventures, can stymie and foreclose that future. So we are here on Earth in a very special place, and we're here at a very special time, and I think that's a good thought to end on, whether you're astronomers or not. Thank you very much. Sure.
Just an aside, I prefer goldfish to dogs because they're lower maintenance.
Yes.
Martin, is it ethical to support people to go to Mars on a one-way ticket? It is true that, it smacks of euthanasia. Seriously. It is true that many explorers in the past have perished, but not intentionally.
No.
Let me just say one thing. One of the PhD students signed up for the one-way trip to Mars, and she did accept it. I don't know if she's here.
I'd like to say two things. I do have this, but I think there'll be rather crazy people like Sir Ranulph Fiennes, dragged a sledge across the Antarctic in winter, and they're prepared to risk their lives for something which they think is an exciting achievement. And I think I think we should cheer them on. I think also, for just the reason you mentioned, they will never be publicly funded. And I think that, but the reason why I think it'll be people like that who go is that NASA or ESA has to bring them back, and that costs much more. Whereas a private company can send them on a one-way ticket if they're volunteers. And I think we should cheer them on. And but it's their individual choice, and we're in no way complicit if it's not public funding. So that's why I think it will only be these private people who will go. Yeah. Susan.
It's really hard, and of course it's two questions. You've given us a wonderfully speculative talk here in many ways, but I wondered, out of all the history of astronomy, what is it that has most excited or inspired you? And in terms of what you think the future technologies will bring us,
Yes.
other than, of course, the vision of avatars, even wiser than you are,
Yeah.
most excites you or moves you?
Yes. Well, I think I've been in the subject for more than 40 years, and I think it's remarkable that going back to actually 50 years, going back to the mid-1960s when I started as a research student, it wasn't clear that there had been a Big Bang at all. Steady-state theory is still credible, whereas now, as we've heard, we can talk about the physics right back to a tiny fraction of a second and pin down the parameters. That's huge progress, and we can understand, at least in outline, how the Big Bang evolved over 13.8 billion years into what we see. I think that's very, very exciting. And we've also found many exotic creatures out there, black holes and all the rest of it. And I'm now very excited about planets around stars and exobiology, and I think that's going to be as exciting over the next 50 years.
How far are we away from developing novel spacecraft propulsion technologies, things like ionic and photonic? Is that science fiction, or is that going to happen?
Well, I mean, I don't think a nuclear rocket is science fiction. I mean, NASA JPL spent a lot discussing a nuclear rocket, and that would allow you to get it out of planets in a few months rather than a few years. So that's not crazy. I should say that Mr. Urim Milner has another project which I do think is rather more crazy, which is to have a huge laser where the laser beam can accelerate a tiny, tiny probe to 20% of the speed of light, which could go to Alpha Centauri, at least possibly in his lifetime. And that is technically feasible. But I think interstellar travel is something for post-humans, not for humans, because, I mean, if you're near immortal and you last for a million years, then a journey of thousands of years is just a doddle. So we should leave that for the post-humans. And of course, maybe they're out there already. Maybe they will be visited. And one thing I should have said is that although I'm skeptical about intelligent life out there, there are some people who think that they've already found it. I mean, I get letters. I'm sure Arnold got letters from people who think that they've been visited by aliens or abducted by them. And when I get these letters, I say two things. I say, well, do you really think that these aliens, having made the huge effort to traverse interstellar space, would they just meet a few well-known cranks, make a corn circle and go away again? It seems unlikely. And I also say they should write to each other and not to me. And perhaps Arnold did the same. Yes. Okay. Yeah.
Martin, these spacecraft going at 20% the speed of
Yes.
light, you've got to be pretty quick with your photography when you get there.
I know. Yes, that's why I find it hard to see how this could be justified. Precisely. Yeah. And also, they're talking about sending something whose total weight is only a few grams. And you've got to not only have your camera and everything else, but also be able to transmit things back to the Earth. And I said how amazing it is to get stuff back from Pluto. This is going to be 1,000 times further away.
There's a few challenges left.
Yeah. So I think this is a post-human enterprise.
Anyone want to have the last question? I think this will be the last question.
This question is based on all the talks this afternoon. What do you think it is that makes astronomers, cosmologists, fundamental physicists such fantastic communicators?
Well, I'm I'm not sure that we are. But I mean, I think seriously, I think in my case, I find it gratifying that I can talk about these subjects not just to a few fellow specialists, but to the wider audience that's interested in these big fundamental questions. Are we alone? Is space infinite? And all these things. And I think it is very important that, that since we are fortunate to be paid to study these, we should meet this public interest as much as we can and as effectively as we can. And I think for young people also it's an entree into science. I think for young people, fascination with space is second only to fascination with dinosaurs. And there's an interesting conclusion there, which is that some teachers think you've got to make science relevant to enthuse young people. That's completely wrong, because nothing could be as irrelevant as dinosaurs, and it fascinates young people. So you've got to develop from the sense of wonder and mystery, which people have when they talk about dinosaurs or when we talk about the cosmos, and then lead from that to more practical sciences. So that's not to answer your question, but it's why I think we should try and communicate and do the best we can. And we should celebrate those people who do it in a big way.
Just before I propose a brief vote of thanks to all of the speakers, let me just say what happens next, if you wish. Please come with us about 100 metres over towards the new building, where there's one thing astronomers can predict, and that is it's getting dark out there. It may not be quite dark enough yet, but I can predict it will be soon. So I believe the first of the light shows on the new building will take place round about 6:30, or perhaps a little bit after if it's a bit too light. So you may have a few minutes to network and chat to people, but do join us for the light show, which I'm sure will be very astounding. And please join me in thanking all our speakers for a fantastic